focus on a spherical coordinate system. In a spherical coordinate system, a point is specified by its distance from the origin, which I will call r, and if I make the plane containing this point and the z axis, so this is r, the distance from the origin to the point. In this plane, if I measure the angle from the z axis to this line joining origin and the point, this angle is given as theta, and the angle this plane, this entire plane makes from the x axis is known as phi. So this point is specified by r, theta and phi. To cover the entire range or entire space, we let r go from 0 to infinity. Theta varies from 0 to pi. That means it varies from plus z axis to minus z axis, and then let phi vary from 0 to 2 pi. And that covers the entire space. So these are going to be the ranges of the variables. Relationship between r, theta and phi with Cartesian coordinates is going to be r, you can see immediately, is nothing but x square plus y square plus z square. Theta is the angle between the z axis and r, and therefore you can immediately see that cosine of theta is going to be given by z over r, or z over square root of x square plus y square plus z square. Third, this r has a projection in the xy plane, which is this red thick line, which is nothing but r sine of theta. And if you have studied the previous lecture well, this r sine theta is nothing but equivalent to cylindrical coordinate s. And therefore, x coordinate is nothing but r sine theta cosine of phi. Y coordinate is nothing but r sine of theta sine of phi, and this immediately tells you tangent of phi is exactly like the cylindrical coordinates y over x. How about the unit vectors? So I am going to have unit vectors in direction r, like this, in direction theta, which is going to be in this plane containing the point and the z axis, is going to be perpendicular to the to r, and like this. If I transport it parallel to itself, it's going to be pointing down like this. And phi vector is going to be like the cylindrical coordinate phi vector, like this, which is perpendicular to r, theta and phi. So let's write this: r unit vector, theta unit vector and phi unit vector. And this forms a coordinate system which is perpendicular. Three unit vectors are perpendicular to each other, but none of these vectors, r or theta or phi, are fixed in space. So they are not fixed unit vectors. So as you change the position, they also change. Let us write them in terms of x, y and z unit vectors. R is pointing this way, and we have already seen that if I take the unit vector, its distance is 1, its z component is nothing but cosine of theta. So cosine of theta z plus projection in the xy plane is sine theta, and its x component is going to be sine theta cosine phi, as we saw in the previous slide. So x component is sine theta cosine of phi in the x direction, plus y component is going to be sine theta sine of phi in the y direction. This is r unit vector. How about theta unit vector? Theta unit vector is perpendicular to r, so therefore it makes an angle, and let me show it by red out here, or make it separately. This is my point. Theta is pointing down, making an angle theta from the xy plane, and therefore in the xy plane its component is cosine theta. So it's going to be cosine of theta, and then again that has a component cosine phi in the x direction, plus cosine of theta sine of phi in the y direction, and the z direction it has negative component, so it's going to be minus sine of theta times z. You can already see that if I take the dot product here, r dot theta, this is 0. This gives you sine theta cos theta, cosine square phi plus sine square phi minus sine theta and cosine of theta. So this is going to be 0. So they are orthogonal to each other. Phi unit vector is pretty much the same like in the cylindrical coordinates, and its coordinates are going to be therefore minus sine of phi x plus cosine of phi y. These are the 3 unit vectors in cylindrical coordinates. How about line element? Oh, first the position vector. Position vector r is nothing but r unit vector r. That's the position vector in cylindrical coordinates, in spherical coordinates. If I am going from one point to the other, I am changing r to r plus dr. I am changing theta to theta plus d theta, and I am changing phi to phi plus d phi. So dr is going to be nothing but d of r unit vector r, and as I said earlier, these are not fixed, so this is going to be dr in unit vector r direction plus r times change in the r unit vector. R unit vector change comes both r unit vector changes both due to change in theta and phi. Remember, what is r unit vector? R unit vector is nothing but sine theta cos phi x plus sine theta sine phi y plus cos theta z. Therefore, dr unit vector I can write as cos theta cos phi d theta x plus sine theta minus sine phi d phi x plus the second term cos theta sine phi d theta y plus sine theta cos phi d phi y, y plus this change, which is minus sine theta z. Look at the terms. This one, which is, and this one. If I take sine theta out, this becomes minus sine phi x plus cosine phi y, and this should be d theta. All right? And look at this term encircled in green. and here, and here. If I take d theta common, I get cosine theta cosine phi x plus cosine theta sine phi y minus sine theta z. And what is this unit vector? This is theta unit vector. So I can write this green thing. Let me go here. I can write this green things combined together as d theta in theta direction. And the blue things, this one and this one, if I take d phi and sine theta out, you're left with minus sine phi x plus cosine phi y, which is phi unit vector. So I can write this as plus sine theta d phi unit vector. Put these things here. So what is the line element that I get? I get line element dl is equal to dr in r direction plus d theta times r in theta direction plus r sine theta d phi in phi direction. That makes perfect sense, because if I look at the coordinate system, if I move in r direction, this distance is dr. If I change theta, this distance becomes r d theta. So that is this line element. And if I change phi, the distance I cover in phi is going to be r sine theta d phi. So this is the line element. Next, let's look at surface elements. Surface area elements perpendicular to r, perpendicular to theta, and perpendicular to phi. Let's look at perpendicular to r first. This element is going to look something like this, where this distance, this is unit vector r, is perpendicular to r, and this distance is going to be distance moved in the xy plane. So this is going to be r sine theta d phi, and this distance is going to be due to change in theta. So this is going to be r d theta. So the surface element I can write in this form is ds is equal to r d theta times r sine theta d phi in r direction. Let's go to the next page. So ds in r direction is r square sine theta. Let me see if I wrote d theta back there. There's a d theta here. So r sine theta d theta d phi, and it's in s direction, where theta varies from 0 to pi and phi varies from 0 to 2 pi. Sometimes this is also written as r square d cosine of theta d phi, where d cosine theta is the integral over, now I can take cosine theta as the variable. So cosine theta varies from -1 to 1. Very easy to see that this is correct is if I take a sphere of radius r centered at the origin, an element, all area elements are perpendicular to s, because area is perpendicular to the radius. So the total area is going to be integral magnitude of ds in the r direction, which is going to be r is fixed, so r square d cos theta from -1 to 1, d phi from 0 to 2 pi, and that comes out to be 4 pi r square. How about area element perpendicular to theta? Let us look at that. If I am taking an area element perpendicular to theta, the distances covered are going to be in the r direction and in phi direction. In the phi direction, the distance covered is going to be r sine theta d phi. In the r direction, distance covered is going to be dr, and this is going to be area element in s direction. And area element perpendicular to phi, that is going to be here, perpendicular to phi, and that is going to be, again using coordinate systems in r, theta and phi, we will have a length element perpendicular to phi in theta direction, which is going to be r d theta, right. So, here will be r d theta and 1 in r direction, and this unit vector is in the phi direction. So, r d theta times dr in phi direction. How about the volume element? Let me first make one volume element and you will see what it looks like. Here in phi direction, so this is in the r direction, this distance, this is like projecting like this onto the center. So, this distance shown by green or shown by red is dr. This distance is moving in theta direction is r d theta, and the distance perpendicular to both is going to be r sin theta d phi. All right. So, these three are the small distances or small height, length and width of the volume element, and therefore, the volume element is nothing but dr times r d theta times r sin theta d phi, which is equal to r square sin theta d theta d phi, sometimes also written as r square d cosine of theta d phi. To understand this figure, you have to imagine a bit or look at a corner of the room and see how you can think of that as the origin and how you can think of theta, phi and r direction. Right. So, this is the three line elements, area elements and volume elements in spherical coordinates. Using these, one can derive expressions for curl by the definition of curl, divergence by the definition of divergence in these coordinate systems also. So, we have derived in the two lectures the line elements, area elements and volume elements in Cartesian, cylindrical and spherical coordinate systems. Using these and using the Stokes theorem and divergence theorem or their definition, we can derive the expressions for the gradient, divergence and curl also in these coordinate systems. We will focus on